All right, so we're on to 7.1. I guess I had forgotten to record this during the actual class, so I'm going to have to run through this without a live studio audience. So we're going to be looking at three-dimensional figures now. Okay, so solids as we call them. So a solid is just a three-dimensional figure closed in some spatial figure, right? And there's some parts to it. We also call them a polyhedron, right? Is another name for it. It has polygons as faces, and it has some type of shape for the base, okay? So the face of a polyhedron is just one of the polygons that form it. Like in this image over here, it's the four triangles that are the faces of that particular pyramid. And the base looks to be a square, okay? So now an edge is just where two of the faces intersect, okay? An edge is where two of the faces intersect. All right, so this face and that face intersect at that edge. There's another edge where they intersect, okay? And they have that labeled over there, okay? Now a vertex is just where edges intersect, okay? So they have one vertex labeled over here. This top vertex at the peak there, we usually call the apex. Okay, it's still a vertex where edges intersect, but we call that the apex. Now we name, in this case, this is a pyramid. We name pyramids and such by the shape of its base. And this looks to be a square base, so we call this a square pyramid. Square pyramid. Okay. And the height of the pyramid is the distance measured from the apex to the base, and it has to be perpendicular. So this, notice it's perpendicular, okay? Notice that that is the height of this particular pyramid. We'll get into more of that later, okay? Let's move on to another solid called the prism, okay? You've looked at these before. Prisms have two bases, all right? And the bases in a prism are parallel, so it has parallel bases. Okay, and parallel edges, parallel bases and edges. Okay, so to identify what the base of a prism is, you look at the two sides that are parallel. We could think of the bases as being translated from one to the other. For example, in this here, it's made up of all squares, right? This base and that base are parallel. One could have been translated to the other. That's isometric, right? So they're congruent. So they're congruent and parallel. So it turns out with a cube, any two opposite sides can be the base, all right? If we look at the next figure over, it's a different type of prism, and you can identify the bases by looking at what parts of it are parallel, and the triangles are parallel. Now, a prism is not always sitting on its base. It's not necessarily how you identify it. Okay, it may or may not be lying on its base. This one, in particular, is lying on one of its faces. We know that this and this are the bases because they are congruent and parallel. They're hexagons, right? So as far as naming these prisms, okay, we name them by the shape of their base. The first one here, well, it's a cube, but to be consistent, we could also call it a square prism. We're naming it by the base. I'm not sure how often you'll ever heard that term used. Most people will call it a cube, okay? But you could call it a square prism. The next one has bases that are triangles, so we call this one a triangular prism. Triangular prism. The bases in this third one are hexagons, six-sided polygons, so we call this a hexagonal prism. Hexagonal. Okay. And the last one there that they have, it looks like a cereal box. The bases are rectangles, so we call it a rectangular prism. Okay. And by the way, again, on this one, like the cube, any pair of opposite faces could be considered the base because they fit the criteria. They're parallel to each other and congruent, okay? So a rectangular prism and a cube or square prism, and any pair of opposite sides could be the base, opposite bases, okay? Now some terms we need to be familiar with here. We know about the bases of the prism, okay? If it's not a base, we call it a lateral face, okay? And if we're talking about a right prism, okay, that means that the height or the lateral sides are perpendicular to the base, okay? They're perpendicular to the base. So if we look at the up top here, right, this would be a right square prism, a right triangular prism, right? We're assuming that is a right angle, okay? And down here below that, they have some actual examples of the right angles written in, okay? So these are all right prisms, okay? This is a right triangular prism, okay? This one would be a right rectangular prism, and we would call this last one a right hexagonal prism, all right? And so again, the common error kids make, right? They include it here, is that you identify the base as the side that the prism is sitting on. That it's not how we do it, okay? It may not be sitting on the base, like this hexagonal prism here. The bases are the congruent and parallel faces of the prism, okay? Looks like one has been translated directly over to the other, okay? Now the height of the prism is always, of course, the perpendicular distance between the two bases, the congruent bases, right? And again, we name the prism by its base shape, and we've just done all that, okay? Now, we talked about right prisms. If it's not a right prism, okay, that means the faces are not perpendicular to the base, right? We call that an oblique prism, oblique. And on the next page, there are some examples. Top of the page 67, right, we have some examples of oblique prisms. Notice that the edges here are not perpendicular to the base. The face sides are not perpendicular to the bases, so those are called oblique. So if you wanted to measure the height of one of these, remember height and base have to be perpendicular. You'd have to kind of extend outside of it, like you see sometimes, okay, to get the actual height of it. Something like that. All right. Now down here, we're getting ready to talk about the volume of prisms. And they introduce this as the stacking principle, okay? So if we have a stack here of CD cases, we know CD cases are rectangular in shape, not necessarily square, right? But if we stack them up, notice that the bottom one and the top one are congruent, okay? So those are would be the bases of the prism, okay, they're congruent. And if you wanted to find the volume, could we not just add up each of those, right, to get the total volume? And the more that you have, I would say the more accurate your volume would be by adding up all the different layers of it, right? So if we have a book with pages in it, okay, this bottom layer would be congruent to that top layer. Those would be the bases of it. And if we added up all the pages from bottom to top, we could call that the volume, right? All the page areas, I should say. Same with a stack of money or whatever that is in the last picture, okay? Now it's important to note that each one of the, say, the pages in this book, each of the pages in this book, or each of the jewel cases or the CD cases in that stack, each single one of those is what we call a cross section. If we were to take a knife and slice this prism open, slice it so that it's parallel to both the bases, the cross section of this one would be a rectangle. This would also be a rectangle. Okay, you have to picture kind of slicing it open, slicing it down, you know, parallel to the base, and opening it up. And the cross section is the shape you see when you open it up. So if we took a knife and sliced it through this triangular prism, the cross section would be a triangle. If we took a knife and sliced this down the in that direction, straight down, parallel to the base. The cross section you'd see when you open it up is a hexagon, etc. Okay. Now all of these cross sections, just like up here with the book pages, will be congruent to each of the bases. Okay. Congruent to each of the bases. And if we added up all those cross sections, we would get pretty close to the volume. But in any case, here's the formula for the volume of a prism. Okay. Now the volume of a prism here is big B. Big B. That's different from the little b's that we use. So you're going to have to start using the distinction between capital B's and lowercase b's. All right. So capital B times H, where B is the area of the base, whatever shape it is, right, times height. But as always, height and base have to be perpendicular. Okay. They use a capital B here because the shapes of each base can be different and they'll have different area formulas. So capital B is the area of the base. Right. Now on the next page, they introduce this thing called the Cavalieri principle. And now in the Regents exams, they like to ask about this every now and then. Here's what the Cavalieri principle says. If you have two prisms, right, and the areas of the cross sections, or the bases, because we know that they're congruent, right, areas of the bases, or the base of each one, are the same, okay, and they have the same height, okay, the same distance between the bases, and the solids have the same volume. So if they have the same base area and the same height, they have the same volume. Here's a couple of examples. Here is a right hexagonal prism. Here is an oblique hexagonal prism. I guess they're trying to indicate that the bases have the same area as each other. Okay, that area is congruent, and their heights are congruent, and they will have the same volume. Now that would also go, they didn't show it here, this would also go for different shaped bases, okay? So let's say this one has a hexagonal base, it's a hexagonal prism, and another one has a triangular base, okay? If the area of the triangular base has the same area as the hexagonal base, and they have the same heights, then the prisms will have the same volumes, even if the base shapes are different. The shapes are different, but their areas are the same, and the heights are the same. The prisms will have the same volume. Okay. Okay. Moving on to another type of prism, but we give it a different name because the shape is unique. If the shape of our prism is a circle, okay, we don't call it a circular prism. We call it a cylinder. Okay. A lot of you may be familiar with cylinders, okay? And we'll get the formula for the volume of the cylinder here in just a moment. But I want you to think of a soup can. Let's say what we have over here is a can of soup or roast beef hash or whatever it is that you like to eat, okay? And we unwrap the label from around it. The shape of that label, as you can see, if we unwrap it from around the can, would be a rectangle. And whatever the height of the can is, would also be the same height as the rectangle. Now this distance around the can, well, it's a circle, right? The distance around a circle is circumference, 2 pi r, and so the width of our rectangle would be equivalent to that, so that's also 2 pi r. Okay? Now let's move on to the formula for a cylinder. It really is still capital B times H, but in this case our capital B, the area of our base, is the formula for the area of a circle. So pi r squared, that's our capital B. So the volume of the cylinder is just pi r squared H, okay? So it's really consistent with, volume equals capital B times H. Our capital B, since the shape of the base is a circle, is just pi r squared times the height of the cylinder, right? And this is, by the way, how you find the displacement of a car engine, okay? So if you have 8 cylinders, right, and you know the radius of each cylinder and the height of each cylinder, you just do pi r squared H, whether it be in centimeters or inches or liters even, okay? And then multiply that by 8, and that's your engine's displacement. Like a 350 cubic inch engine has 8 cylinders, right? And the volume of all the 8 cylinders adds up to 350, or which would be equivalent to like a 5.7 liter. You're measuring it in cubic centimeters, or in the metric system. Here's a couple of objects. This would be a right cylinder, which is what you would find in your automobile. And this would be an oblique cylinder. So there we go. So we have prisms and cylinders. They're really the same general formula for volume. V equals capital B times H, or big B times H. Just the big B in a cylinder, since it's a circle, ends up being pi r squared. Okay? Need to give you a couple of notes before we move on. So define a couple of terms. A plane is just something that extends infinitely in 2 dimensions. Extends infinitely in 2 dimensions. Okay? And you're familiar with certain examples of planes, like the XY coordinate plane. That fits that definition. Okay? Or you may have seen it sketched out something like this, right? And roughly, it's not the best image. Examples, in the room around you, might be the wall, ceiling, the desktop in front of you, kitchen table, etc. Okay? And one other item we need to think about, as we're thinking about cross sections, are conic sections. Okay? These have been studied for about 1,000 years. Conic sections. So we start with a cone, okay? And we intersect a cone or a plane with a cone, okay? Conic sections are just the shapes that are found when we have a cone intersected by a plane. Think of the plane as a knife blade. Okay. Now, these are kind of tricky to draw, so I'll draw one of them, sketch it, and then I'll put up an image that shows the rest of them. Now, the classic conic sections, there's 4 of them. There are 1 or 2 others that could be formed, but I guess they were kind of boring. So let's start with a cone. Let's see if we can take a plane here, sketch it in roughly. I'm not super great at this. I'll do my best. Some of you are much more artistic than I am. So let's draw a plane, kind of slicing this through. Right. And in this case, we slice it that way, we get an oval, right? Or we could slice with the plane parallel to the base of the cone and get a circle. So there's 4 conic sections. There is the circle, the oval, or mathematically we call it an ellipse. Okay. There's also a parabola. You know what that is because you studied in algebra. And something you'll get to in a later math class called a hyperbola. All right, so let me bring in an image that might be a little more clear here. So here's a little better image, I think, right? And we have to kind of think of some of these as 2 cones standing on top of each other. Okay. In the first cone, here's our parabola. Okay. We have a parabola here. You know what that looks like. It's kind of like a U. If we slice one of the cones at an angle with our plane, we get the ellipse. If we're parallel to the base, we get a circle. Now a hyperbola will be when we slice through both of the cones and get this section and that section. And we'll save that for a little bit later for math class. Now we can also get a triangle, though it's not one that's considered too much, right? If we cut one of these cones kind of like this and slice it perpendicular to the base, that cross section will be a triangle. And so now we are ready to move on to some Regents questions. All right, so the Regents questions. Let's look at the first one here. Two-dimensional cross section. So you can took a knife and sliced it, okay, of a three-dimensional object. If the cross section is a triangle, what cannot be, the key word is not, be the three-dimensional figure or object that you sliced. Okay, I'll give you a minute to look at those. We'll be back with you. So I already know a cone could have a triangular cross section. Like if you take a look at this one here, we kind of sliced it, down. You'd have a triangle. So it's handy to use an image in another problem. Okay, so it can be a cone. Obviously, it could be a pyramid, rectangular prism. Yeah, if you've got at the correct angle from one corner to the other, you get a triangle. So it'd be a cylinder. There's no way you can get a triangular cross section of a cylinder. On to number 2. William is drawing pictures of cross sections of the right circular cone, which cannot be a cross section of a cone. Well, we know there's 4 main ones that are studied, and of course we also know a triangle can be added to that. So this one would be the parabola. We know that's one of the conic sections. That's the ellipse. We know a triangle can come from it. So the only one you can't get from a cone is a square. Number 3, a right cylinder. It's cut perpendicular to the base. Okay, so you have to picture that. Maybe like you empty out a can of roast beef hash onto your plate. You've ever done that? And then take a knife and sliced it from top to bottom. Okay, so it might look like this. Right, and then you sliced it straight down like this. Okay, your plane went through there. You are going to end up with perpendicular to the base. That's right. That's kind of key. Sliced it perpendicular to the base, so you'll end up with a rectangle. Number 4, we have a plane that intersects a hexagonal prism. The plane is perpendicular to the base, so a little bit like the one we just read. Which two-dimensional figure is a cross section? If we slice it perpendicular to the base. Well, it's a hexagonal prism. I'm not going to try and draw that. That's kind of a mess. But wouldn't it work just the same as a cylinder? If we sliced it from top to bottom perpendicular, you'd again end up with a rectangle. Moving along. Number 5. So this has to do with the Cavalieri principle. Cavalieri, sorry. All these years I still can't pronounce it. So Sue believes the 2 cylinders have equal volumes. Is she correct, and why? Well, according to the Cavalieri principle, if 2 cylinders have bases with the same areas and they have the same heights, then they have the same volumes. So really what you need to show here is that the areas of the bases are congruent. Bases are circles, right? So this base here, and you have to show this work, would be to circle, so pi times 5 squared, which is 25 pi. And over here, it's got a radius of 5, right? So it'll be the same thing. So that, we'll call that base 1, base 2, equals 25 pi. And they both have a height. Remember, the height is perpendicular of 11.5 meters. So our answer is that Sue is correct. So Sue is correct. We have to have that part of it. Right? But why? Explain why. Well, say since the cylinders have the same base area and heights, they must have the same volume. Since the cylinders have the same base areas and height, right, they must have the same volume. Must have the same volume. All right. And number 6, our last one, is a lot like the one we just looked at, except there is one thing we have to include, and it has to do with the way they word it. So we have 2 prisms, 2 triangular prisms, and it looks like they have the same height, okay? 5, length of 8. So it says to use Cavalieri's principle to explain. So in your explanation, you're going to have this phrase, Cavalieri's principle. All right. But first, like the last one, we know the heights are the same, so let's calculate the area of each base. So base 1 here, it's a triangle, so 1/2 times 8 times 5. Half of 8 is 4, 4 times 5 is 20. For base 2, it's a triangle again, 1/2 times 5 times 8. Half of 8 is 4 times 5 is, again, 20. So they have the same base and the same height. Okay? So our wording this time might be, by the Cavalieri principle. Okay? By or according to, whichever. The Cavalieri principle. Right? See, because they said use that in your explanation. So that's what we're doing. Okay? The prisms have the same base area and height, or since the prisms have the same base area and heights, their volumes are equal. Volumes are equal.